Welcome to Structural Dynamics class. In this class, we are going to study vibrations of continuous systems. So, continuous systems means where the mass is distributed continuously. So, earlier we had studied single degree of freedom systems and then multi degree of freedom systems. So, multi degree of freedom systems are something like where we can do the lumping of masses at different stages in the building. So, if you take a building like this, so we can assume that, so this is floor 1, floor 2, floor 3, floor 4 and floor 5. So, slab is mostly concentrated at floor levels, mass is concentrated at floor levels or weight is concentrated at floor levels. So, we can lump the mass here, lump the mass at this level, lump it here, here and here. So, that is how we study multi-degree of freedom systems. But in continuous systems, what happens is mass is distributed continuously throughout the structure, throughout the height of the structure. So, for example, say a tower or a chimney, okay. So, communication tower or chimney. So, for that studying vibrations or understanding the solution or the response to the given ground motion or any wind vibration. So, we need to employ different techniques, not the same technique as we have used in multi-degree of freedom systems or single degree of freedom systems. So, let us understand how we find the solution for the equation of motion for continuous systems. So, a special type of structures like say cooling towers, bunkers, silos are considered as continuous systems where mass is distributed continuously. Some of the continuous systems may have different types of profiles like rectangular, trapezoidal, hyperboloid, etc. So, their response due to dynamic loading varies for different profiles. So, what profiling is a deflection profile? So, we need to understand that also first. So, as I discussed in the earlier classes in multi-degree of freedom systems, so when say a tower or a structure like this one, tall building like this one is vibrating, when it is vibrating, when we want to say that displacement or deformation, we need to take two variable quantities. One is at what place we are talking about and in what time we are talking. So, for that we need to tell, say in multi-degree of freedom system, space can be located as say first floor, second floor, third floor and fourth floor like that, and time is continuous. But in continuous systems, this location also is continuous, time also is continuous. So, these two things we have to discuss in this one. So, for that let us take say a structure or a member, something like a shear beam. So, here we can see that so this is positive u axis, u is the displacement, and then if we take the infinitesimal cross section or infinitesimal length which is of dx, and rho is the mass density, ax is the area of cross section, this is x axis. So, throughout the length of the member or the height of the structure. So, now let us write the equation of motion for this one. So, how do we get? So, when the structure is vibrating, so when it is moving down, then we know length is dx, that is infinitesimal length. So, we know that moving mass generates inertia force opposing the motion. So, now what is inertia force? Inertia force is mass times acceleration. Since I told you u is the displacement, so u dot will be velocity or u double dot is acceleration. So, u double dot is dou square u by dou t square. So, this term is acceleration term, and a dx, a is a cross section area and dx is a length. So, a dx is volume multiplied by mass density. So, we get mass. So, this term is representing mass and this term is representing acceleration. So, mass times acceleration, m times u double dot. So, this is inertia force which is opposing the motion. Now, if we write the shear force which is acting upwards, and on the other side if we write, so the shear force will have some like additional value. So, q here, q plus dq. If we write equilibrium equation of this one, so q plus dq downward minus rho a dx dou square u by dou t square is upwards minus q upwards minus is equal to 0. So, sigma v, sum of all forces in vertical direction should be equal to 0. So then see this q and q will get cancelled. So we are left with, so if I take these terms in onto the right hand side, so if I rearrange the terms, rho a dx is mass times acceleration is equal to dq. So change of shear, so dq should be equal to that value. Now if we write from this one, so what we can do is rewrite this, dx can go down, dq by dx is equal to rho a dou square u by dou square u by dou t square. So this is equation number 1. Now let's take like from the shear relationship. So if we apply shear force q and then deflection is delta, so what we can write is delta deflection is equal to QL by AG. So Q is a shear force, L is the height or length of that member. So QL by AA is a cross section area, G is a shear modulus. So from this we can write Q is equal to AG by L into delta. So we already know that delta by L. So if we take from this one, delta by L is equal to, so delta is say deflection, L is the length. So this we are writing say infinitesimal deflection by infinitesimal length. So dou x is infinitesimal length of the member, and delta u is the infinitesimal deflection of this delta x length. So if we substitute delta by L as dou u by dou x, so we get q is equal to ag multiplied by dou u by dou x. So from the above equation 1, if you look at this equation, we need dq by dx. So that means what? If we differentiate this once, what we get is dq by dx is equal to ag into dou square u by dou x square. Then substitute in the earlier equation, equation number 1. Then we get ag delta square u by delta x square is equal to rho a delta square u by delta t square. So that means what we get is, if we rearrange these terms, delta square u by delta x square is equal to rho by g delta square u by delta t square. So this is wave equation. So u xx is equal to c square u tt. Actually c represent wave velocity, which is equal to under root rho by g. Now we need to solve this. So this is a differential equation. Now governing differential equation of vibration of a shear beam. Okay, shear beam which can be equated to a tower or any building, okay, high rise structures like that. So now we need solution. So how do we get solution of this one? So the governing differential equation of shear beam is known. So shear area is dependent on the shape factor, and for rectangle 0.8 of A is a shape factor. Now we are using say u, which is the displacement function, as a function of x of x and t of t. Okay, we need to use in this one variable separable method of solving differential equations for finding the solution of this governing differential equation. So in this one, if I differentiate it once with respect to x, so I get x prime t. If I differentiate it twice, I get x double prime t, because t is not the function of space. So that's why I get x prime t and x double prime t here. So again similarly, if I differentiate it with respect to time, x t dot u double dot is equal to x t double dot. So I have two quantities. Now if I substitute in the governing differential equation, that will delta square u by delta x square is equal to rho by g delta square u by delta t square. If I substitute this in the equation, what I get is this term in place of this one. So I get delta x double prime t is equal to rho by g x t double dot. So I can rearrange this one, x double prime by x is equal to rho by g t double dot by t. So what I do is, this rho by g x double prime by x is equal to t double dot by t dot, t double dot by t, not t dot. So t double dot by t is equal to minus omega square. So I am equating to some constant. So then if I do rearrange this one, t double dot by t is equal to minus omega square. So that means what? T double dot by t is equal to minus omega square. That means t double dot plus omega square t is equal to 0. This is one equation. G by rho x double prime by x is equal to minus omega square. So this one is something like single degree of freedom system equation of motion, and the solution for that is known to us. So T of t is equal to a cos omega t b sin omega t. So we already know this one. Now let us solve this one, second equation, which is in space variable. So g by rho x double prime plus omega square x is equal to 0. Now if we divide the second term by the first term and first term by again first term, so what we get is x double prime plus omega square by g by rho into x is equal to 0. So the possible solution of this could be x of x is equal to c cos lambda x plus d sin lambda x. So this lambda x will come from this function. So lambda square is equal to omega square by g by rho. So this. Then let's find out the constants in this one, c and d. Now as we know, if at x is equal to 0, x of x should be equal to 0. So that means what boundary condition will be applied there. So at x is equal to 0 and x dash also should be equal to 0, because we are talking about the shear beam. So in shear beam what happens is deflection is 0 and slope is also 0. It is something like this. Beam is of this nature, and what happens is you can see here at x is equal to 0 deflection is 0, and at x is equal to L or x is equal to 0 you can get slope also has to be equal to 0. X dot prime is equal to 0, x also should be equal to 0 at this point. So substituting the first boundary condition, x of 0 is equal to 0, so that means c constant is 0. Okay, in this one, okay, c constant is 0. And then x prime means you differentiate it once. So then what we get is minus lambda c sin lambda x plus lambda d cos lambda x. So since already c is 0, so we are left with only x prime is equal to d lambda cos lambda L. So this d lambda cos lambda L we need to find out, because this x prime L is 0. Oh sorry, the boundary condition what we are using at this location is x prime L, not 0. So d lambda cos lambda L is equal to 0. D cannot be equal to 0. For non-trivial solution, lambda also cannot be 0. So what should be 0 is cos lambda L should be equal to 0. So that means what, lambda L is 2n minus 1 into pi by 2. So lambda is 2n minus 1 by L into pi by 2. So lambda square we already know, omega square by g by rho. So if we equate these two, so what we get is omega. So the omega value we get. So then back substituting omega, pi by 2 2n minus 1 by L into under root g by rho. So x of x, finally the value is d multiply by lambda multiply by sine 2n minus 1 into pi by 2L into x. So if we substitute x values at different points of 0 to L, say x is equal to ranging from 0 to L. So if you substitute this one, we can draw the mode shapes. As you can see, if n is equal to 1, we get this. First, this is equivalent to first mode shape. If n is equal to 2, so this is second mode shape. If n is equal to 3, this is third mode shape, and n is equal to 4, this is fourth mode shape. So first mode shape, second mode shape, third mode shape, and fourth mode shape. And this one is similar to our mode shapes in multi-degree of freedom system. So if you just rotate this one and look at it, so this is the first mode shape of the structure, this is second mode shape of the structure, this is third mode shape of the structure, and then this is say fourth mode shape of the structure. So like this. So first, second, third, fourth mode shape, as we got in multi-degree of freedom systems. In continuous systems also we can get as many number of mode shapes as possible. We only need to substitute value of n and evaluate at any point. So this mode shape will give us a deflection profile of the structure, and then we need to solve the time function. So that is, say x of x we are getting, and we need t of t. So this is the overall displacement. So what we had discussed in multi-degree of freedom system is x comma t is equal to phi q. So this t is representing q term and x is representing phi term. So now how do we use this phi term, that is a deflection profile, and find the response of continuous systems? So that we will discuss in the next class. So what we discussed in this class is vibrations of continuous systems. So, vibrations of continuous systems cannot be solved by single degree of freedom systems equation of motion or multi degree of freedom system equation of motion. So, what we need to do is we need to write an equation of motion for the continuous system which will be in the generalized coordinates. So, in that we have understood how to write the equilibrium equation for a shear beam, and then how to find a solution of that, and then how to evaluate the mode shape for a shear beam. That's what we have understood in this class. In next class we will try to find out how we make use of this mode shape and write the equilibrium equation in the generalized coordinates.